Hello, lovely humans, Jen Foxbot here. In this episode of Math Mondays, we're continuing our exploration of electrodynamics, or charges that move. Woo! Technically, we're still on electrostatics though, but we're getting there. Okay, this is actually going to be our last kind of official video in electrostatics before we get to more topics. So in this video, what we'll do is we will look at the electric potential, and we will work through where the electric potential comes from. So we'll basically kind of derive an equation for the electric potential. Cool. Okay, so let's get started. Where do we start? We're going to start with the curl of the electric field. The curl, you say? What? Well, remember, when we have vectors or fields, we can draw field lines that represent the direction of those fields. And so we can draw electric field lines of a point charge like so. Well, technically these should all be the same length. Okay, so if this were, say, moving water, we could drop a little leaf and the leaf would float outward at any point we dropped it. If we had a field that was more like this, and we dropped the leaf somewhere, the leaf would be rotating. And so in this case, we would say that the field is divergent, but there's no curl. And in this case, we would say that there's no divergence, but there is only curl. So the leaf just kind of moves around and around. So because this is, well, what our electric field looks like, what the electric field lines look like at least, we can kind of say without actually calculating the curl that, well, wait, the curl of the electric field would be 0 because this is the picture of the electric field, not this. Not that. So yeah, basically, pictures are super useful. Yay, we're done, right? Well, not quite. So I do actually want to run through the mathematics because I think it will be really helpful. So let's start with a simple case of a point charge at the origin. Okay, so I'm just gonna repurpose this, and we were gonna draw a coordinate system so that our point charge, our green point charge, is at the origin. And we're gonna ask, let me make sure that I get the phrasing right. What is the line integral from an arbitrary path, to some random path, let's say from point A to point B. We're going to go from here to here, and we are going to add up the contributions of the electric field along this path. So that equation is going to be from A to B, E for electric field dot dl, where dl is our infinitesimal displacement vector as we go along the path. And so the electric field for a point charge at the origin, I hope you know it by now. Okay, say it with me if you do. 1 over 4 pi epsilon naught q over r squared in the r hat direction because it is divergent. And remember, I didn't draw it like a sphere, but it radiates outward like a sphere, not a flat circle. It's 3-dimensional. It's hard to draw though. So what we want to do is we want to use spherical coordinates because this will be way easier. Okay, so dl in spherical coordinates is dr in the r hat direction plus r d theta in the theta hat direction. Ooh, am I gonna have space? Plus r sine theta d phi in the phi hat direction. And so this dot product, we have an r hat dot dr, an r hat dot theta hat, or dr r hat, and an r hat dot phi hat. So r hat dot r hat equals 1 because they're parallel. R hat dot theta hat equals 0 because they're perpendicular. And r hat dot theta hat is also 0, again, because they're perpendicular. So these two components of dl go to 0, and what we're left with is the integral, well, we can pull out 1 over 4 pi epsilon naught integral from a to b of q over r squared times dr is the only component of dl that is left. And this is going to give us a negative 1 over 4 pi epsilon naught, because remember, 1 over r squared equals r to the negative 2. And this is going to be q over r from ra to rb, where ra is defined as the distance from the origin to point A, and RB is, that's a crooked line, that's okay, the distance from the origin to point B. Okay, so we end up getting negative 1 over 4 pi epsilon naught q over final minus initial RB minus q over RA. And if I want to get rid of this minus sign, I can just go like that and swap these. Cool. Okay, so that's kind of interesting, but why does this matter? Well, wait a second. Let's ask, what happens if RA and RB are the same? In other words, if we start at A and we're like, wait a second, I want to keep going. I ended where I started. So if your starting point is the same as your ending point, then this goes to 0 because you get, well, q minus q, or well, q over RA minus q over RA is 0. And so you end up along a closed path. The line integral of the electric field along a closed path is 0. Hey, wait a second, I think that there's a theorem or something that has to do with this. Hey, yeah, there is. So Stokes's theorem says that if this is true, then the curl of that vector is also 0. Woo, we did it, yay. Okay, cool. Okay, we're done, right? Well, wait a second, you might be saying, you only did this for a very specific case of 1 point charge at the origin. Fair enough, but it actually doesn't matter where you put the charge, whether it's at the origin or not. You could put it somewhere else, you will still get this result. And because of superposition of the electric field, you can also show that it holds for many charges. Basically, again, superposition is the whole, like, the total electric field can be just summed up with all the different charges. So I'm not going to write that out, but basically you can replace this into here and show that it holds true for many charges as well. Okay, so this is actually where the electric potential comes in, because when this is true, then we actually have a very special vector. So the electric field, it can't be any equation. So for example, we could never have an electric field that was, say, y x hat. That doesn't work, because for this to hold true, the partials of the electric field components must be equal to each other. So for example, this, I'm just going to do one component, but it's true for all of them. And so when you take the partial of this with respect to y, you are going to get 1. But then in the okay, so we'll actually do it. So then this equals 1, but then the partial of the y component is 0 because there is no y component. So you get 1 equals 0, which is not true. Foo. Okay, so this limits the types of formulas that we can have for the electric field. And there is another theorem that tells us that when this is true, when you have the curl of some vector field equals 0, then that vector field can also be written as the negative divergence of some scalar function v. So there's no vector on the top of v. This is a scalar. Whew, we're done, right? Okay, well, but why do we care? Why do we care about the potential? We just spent all of this time learning about the electric field and learning how to calculate the electric field, and now you're telling us that we don't need to bother with the electric field, we just use the electric potential. Well, kind of. It's all about finding the right equation for using the right tool for the right job, right? So basically, this is really nice because if we can find the electric potential, then we don't need to worry with all of the different components of the electric field, and we can simply take the divergence of this scalar value to get the electric field. And again, oftentimes electric potential is enough. Quick note on terminology. Potential, the electric potential, is not the potential energy. Just going to leave that there. It's a very different term. And the units of potential are joules per coulomb, which are defined as a volt. I think that this is kind of confusing because the potential uses the letter V for it to represent it, and the volt is also with the V, so electric potential has units of V. That's pretty fun. But the key point that I want to make here is that oftentimes it's way easier to find the electric potential, and then if you need to get to the electric field using the potential. So if you can find V, do it. Cool. All right. So I'm going to leave it there for now. I hope that this was helpful. Let me know if you have any questions on the motivation or kind of the derivation behind electric potential. And yes, in the next episode, I will do a quick summary of the electrostatic boundary conditions, and that will kind of summarize all of the equations that we have covered in electrodynamics thus far. Woo! All right. Thank you for watching, and we'll see you next time. Bye!